Okay, welcome everybody. Welcome at this, what is called a parallel plenary session this evening. It is my great pleasure to introduce to you Professor Brett Ninness, who will deliver this plenary speech. Brett Ninness got his Bachelor's of Engineering, Master's of Engineering and PhD degree all from the University of Newcastle in Australia. And he's currently a professor in the School of Electrical Engineering and Computer Science at that same university in Newcastle. Research interests are in the areas of system identification, as we all know, and stochastic signal processing. He is the editor-in-chief for IET journal Control Theory and Applications, and has been serving Ifac in several capacities. In the editorial boards of Automatica, but also, as we all know him, as the chair, together with Håkan Hjalmarsson, of the 14th Ifac Symposium on System Identification that was held in Newcastle in 2006. And he also served as chair of the Technical Committee 1.1 during that same triennium. It's my great honor to welcome Brett here and to announce his lecture of today, which is called Computational System Identification. Let's give him a big hand.
Well, thanks, Paul, for that introduction, and thank you to the conference organisers for giving me the opportunity to give this presentation. It's a great honour, and I very much appreciate it. And thank you to the audience. I know you had two parallel plenaries to choose from, and I would actually like to see the other one myself. And I know it's been the end of a long day, so you're probably also relaxing is probably also an attractive option. So thank you. The title of my talk mentions computational system identification, but more broadly, the question I want to touch on today is how might we expand our capability in the area of system identification, and in particular, how could we do that by usefully employing recent advances in cheap desktop computing power. Now, the examples and thoughts along this theme that I'm going to be talking about today involve joint work with Adrian Wills and Soren Henriksen from the University of Newcastle, and also Thomas Schön from the University of Linköping. Pardon me. Now, system identification has existed in a subfield within automatic control for at least 30 years now, so it can be considered quite a mature field. As a result of all that work, the bulk, but not all the methods that we use in that area can be divided into two basic camps: statistically based methods and realisation based methods. And within the statistically based methods, we have maximum likelihood, prediction error methods and similar. And the algorithms that we employ now are ones whereby typically we're trying to minimise some normal-like function of an error. That involves a gradient-based search, so we need a search direction. That involves solving some linear equations that depend upon a gradient, which involves filtering operations. So the basic computational tools we need and employ nowadays are those of numerical linear algebra. Realisation-based methods, well, there's various flavours: FORCID, canonical correlation analysis, MERSP and others. And again, linear algebra type tools are the ones that we employ to solve least squares type problems and do projections. So as mature as our state is, it relies fundamentally on computational tools which basically boil down to MATLAB / and the way that it's implemented, and linear filters. In addressing the question of how might we increase our capacity, I'd like to do that within a theme of what can we do in a minute, because I think a minute is a reasonable amount of time to wait for an answer, and so I'd like to figure out what could we do in a minute with modern computing power available to us. So to be concrete about that, here's a very simple example. A fourth order system which is randomly generated, excited by 1,000 data samples and simulated. And to make it interesting, let's put some measurement noise on top of it, put it in an appropriate format for the MATLAB system identification toolbox, and fit a fourth order output error model. This is an easy problem. It takes me half a second to get an answer. And this was done on a processor with roughly a 3 gigahertz clock speed. So in this day and age, solving this sort of estimation problem is very easy for us. It only takes us half a second out of our minute. And if we'd gone back a decade and just scaled back according to available processor power, it still would have been a very easy problem. It would have taken us only 2 seconds. Go back 2 decades and it would have taken us about a minute. And I can remember doing this at the start of my studies, and everyone was happy to wait about a minute to get an answer to this sort of estimation problem. We can do it a lot faster now, but what does that really gain us? Or put another way, what could we do now with our extra 59.5 seconds if a minute is a reasonable amount of time for us to wait to do something in system identification? Now, at the same time that clock speeds haven't increased dramatically over the last decade, for example, the number of transistors that are available in desktop computers has continued its dramatic rise. Now, this has typically gone into multi-core capacity in computers. So another question that I think is raised by this is, how do we use these extra transistors? The algorithms that we're currently employing that are scaling just with clock speed aren't scaling with these numbers of transistors that we've got available to us. So these are the questions I want to touch on today. And I like concrete examples, so I'm going to give you some concrete examples that we can discuss. Perhaps we could use this extra capacity to look at new estimation methods that we don't typically use, such as Bayesian conditional mean type estimates. Perhaps we could use this capacity to come up with different ways of computing error bounds on estimates, such as computing posterior distributions. Perhaps we could use this capacity to look at the suitability of our model for whatever purpose we want to use it for, such as control design. Perhaps we could use it to look at richer model structures that aren't addressable via our current suite of techniques. And I'll give you examples of all these in the talk to follow. So to kick off the discussion of that, let me modify my first example, which was a random fourth order one, to be a little bit more specific. No longer is it got a random input, it's got a step input. I've only got 100 data samples on the output, and I've put a fairly heavy noise corruption on here, which is uniformly bounded from minus kappa to kappa, such as might occur, for example, if you've got some sort of quantization error in your sensor. Well, we solved that before via a prediction error method, so we can certainly solve this again via a prediction error method. But probably everyone here is very experienced with doing this, and we'll look at this and say, well, you don't have very much data, and it's quite heavily noise corrupted. What sort of errors are you likely to get? Well, I examined that by taking 20 different noise realisations here to add to this noise-free step response, to get 20 different realisations of the noise, and for each of them, I computed a prediction error estimate. The red here is the Nyquist plot of the true system, and the black lines here are the Nyquist plots for each of the 20 estimates. And you can see that, as feared, there is quite a bit of variability here. So when faced with this sort of estimation problem, we might want to try and minimise this error. So, for example, minimise the mean square error in our estimates. So that's a question of, given the data, how can I process the data via some function to give an estimate that minimises the squared error? Is that possible? Is there an estimator theta that does that over all possible choices of ways of processing the data? Well, as we know, yes, there is. It's called the conditional mean. And so I tried that, and for the same 20 data sets, I computed the conditional mean estimate. And you can see that, sure enough, as the theory promises, it gives us much lower variability in the estimates, especially when you compare it to the prediction error estimates. So for this particular problem, which is characterised as being short data and noisy, there might be some utility in considering an estimation method that we typically don't use as part of our system identification toolbox. And there's probably a good reason for why we don't use it. To compute this conditional mean, you need to evaluate a multidimensional integral. The dimension of this integral involves, in this case, 4 denominator parameters plus 5 numerator parameters plus a parameter to estimate this noise variability here, kappa. So it's a 10-dimensional integral that I need to compute to get those conditional mean estimates. Okay, so another thing we could look at if we're looking at posterior distributions is we could look at the question of error quantification. And one way of quantifying error would be to look at the marginal distribution for a given parameter as our quantification of error. Now, again, that's going to be a multidimensional integral, of dimension 1 less than I had before, a 9-dimensional integral, but it can be computed. Here it is for one particular data set of those 20. The blue line here is the marginal posterior density. And I think it's interesting because it hasn't relied on any asymptotic in data length arguments. It's not relying on a central limit theorem. So this density, provided I've computed the integral accurately, is exact for that short finite data length that I've got available. The red is the true parameter and the green is the conditional mean. But it does involve a large integral that needs to be done. And you need to do that for each of the parameters that you want to get an error quantification for. So we're looking at quite a high computational load. Suppose we want to use this model for a particular purpose, such as to design a controller. Well, here in blue is the response, the open loop response of my conditional mean estimate for one of those 20 data sets. And you can see it's got a bit of an oscillatory response. And I've considered the situation of designing an LQG controller for this system. And this is the response of that LQG controller on this nominal plant, which I've estimated. And if I was very brave, I could immediately go and implement that controller on the particular system that gave me this observed data here. But of course, that would be a brave action because there's no guarantee that I'm going to get this achieved response on the true real system. This is only the estimated system, the response on the estimated system. What I'd probably like to do is come up with some measure of how robust this design is, which takes into account the uncertainty in the model that I've got. And people have been researching this for many years now, so there's many ways of addressing this. I'd like to look at one very simple suggestion of, well, could I work out what the posterior phase margin is associated with this controller, this data, and an assumption of a fourth order model? What does that density look like? Is it even computable? Yes, it is. Here's what it looks like. If I was going to implement that controller, I'd be in a situation where on the nominal plant I'm achieving about a 25-degree phase margin, but you can see there's very significant probability that I'm going to achieve much less phase margin than that if I actually achieve it. And there's certainly even a non-zero probability here that I'll have an unstable system. And I think a lot of people would look at this and say, look, Brett, it's a bit risky for you to deploy this controller. You could get quite substandard performance with quite a high probability. The obvious strategy at this point is to detune the controller, go for a slower response and hope that you get some robustness. So you pay a price here and hope you get a payoff. But we can certainly see the price that's been paid in degraded performance. What's the payoff? Well, we can judge that by looking at the associated posterior density now for the phase margin. Much greater phase margin for my nominal system, and now fairly low probability that I'm going to get any phase margin less than 20 degrees if I actually deploy it. So this looks like a much safer design to actually go away and deploy. The question is, of course, how are these posterior densities computed? Once again, numerical integration. So in all these examples, there's a common theme of using the fundamental tool of numerical integration to look at these different methods, which is quite different to the numerical linear algebra tools that we know and love and are very familiar with in system identification. So let's have a look at numerical integration. Well, all of us meet numerical integration in our undergraduate degree and know that if you want to do one of these things, you break up the region over which you want to integrate into m points, and then you use something like Simpson's rule or the trapezoidal rule. And these methods work terrifically well. With Simpson's rule, if you increase the number of grid points by an order of magnitude, you get 4 extra digits of accuracy in your answer. So it's a method that converges quite fast. And you can easily illustrate that once again in MATLAB. Let's look at an integrand which is 4 times the area under the quarter circle of radius 1, and hence we know has answer pi. It's a couple of lines in MATLAB to investigate that integral, or compute that integral using Simpson's rule, and you can see you can get the answer to 10 decimal places in 1/100th of a second. So numerical integration, at least on first glance, need not be a daunting thing for us to have a look at in terms of new methods in our field. But that's for computing a scalar, a function only of a scalar variable. What happens if we go to multidimensional integrals, which we need to do? Well, that means we're going to have m grid points now in each of n, or as many dimensions as we've got parameter values that we're integrating over. So I've called that n theta. So that means the total number of function evaluations we're going to have to do if we're going to do numerical integration blows up with the number of grid points raised to the power of the number of parameters, which can blow up very quickly. If I've only got a third order model, which involves 7 parameters, I'll need to do 10 to the 10 function evaluations if I've just got 30 grid points in each dimension. And 30 grid points is not a tremendously large number. Now, we can only wait so long for an answer, and I've posed waiting a minute as what might be reasonable for waiting for an answer. So that imposes a limit on the number of function evaluations we can do, the capital M we can have. So if that's fixed, we've got to decrease the number of grid points we've got in each direction, which then decreases our accuracy. So if we look at convergence now in terms of how it proceeds with number of evaluations we can afford to do, then the rate at which the convergence occurs can drop quite quickly as the dimension of the integral grows. For that fourth order example, where n theta, the number of dimensions, was 10, we're decreasing at a rate which is slower than the 1 on the square root of m, which is a fairly slow convergence rate. Is there any solution to this? Or put another way, are there other ways I could spend my m integrand evaluations to do this integral? Well, yes, there are. I could employ the strong law of large numbers. Strong law of large numbers is a law which I guess all of us are familiar with, which says if I can draw vector random numbers from a given density P and I evaluate a function f at those independently chosen random draws, then the average of those evaluations converges to the expected value, which is an integral. So I can flip that around and say, well, this is a way of doing integrals. If this is the integral I want to compute, I just need to take random draws from the appropriate distribution and form an average. Now, in doing this, I may get lucky, and this might give me an accurate answer, or I might get unlucky, and I get an inaccurate answer for the particular random realisation run I get. So I'm taking a gamble, and this method is therefore known as Monte Carlo integration in reference to the famous casino in Monaco. Whether I'm unlucky or lucky depends upon how the variability of this estimate of the integral decreases or varies as I take more and more function evaluations. And if the draws are independent, this variance decreases at a rate of 1 on m, and hence the absolute error in my integration will decrease at a rate 1 on the square root of m, which, as I've said earlier, is quite slow. But the key point is it's independent of the dimension of x, and hence independent of the dimension of the integral that I'm trying to compute. It doesn't keep blowing up as the dimension of the integral keeps getting larger. It's not a panacea. This method of integration is used in many areas of science and engineering, and in particular it's used very heavily in statistical mechanics, where Alan Sokal, who is very famous in that field, is famous for saying, look, this is an extremely bad way of doing things. Only use it if everything else is worse. How does it look for a simple example, our quarter circle example, but now with the radius slightly less than 1? Well, I pull draws from a uniform distribution from 0 to 1, throw them into my function here, and take the average. And that will give me an estimate of the area. But I notice that I've got a few draws here which are sort of wasted. And as the radius drops, more and more draws are wasted. this uniform distribution isn't perfectly adapted to the thing I'm trying to integrate. The effect of that is I will get more variability in my estimate. I'll get less accuracy. And I can examine that by looking at the error in the answer I get, but normalised to what the true answer is. And you can see that as promised, it drops at rate 1 on m, and hence the absolute error drops at rate 1 on square root of m. But with a constant out the front here, that can be very large. So I can get a very poor answer if I'm not careful with what random number generator I use for the particular integral that I'm interested in. And once again, this can get worse. This is a problem that gets worse with higher dimensions. I could be perfectly well adapted in each of these dimensions, but still get draws in here which are wasted. Furthermore, in our case, we want to actually pull random number generators out from a specific density so we can compute expected values. So for two reasons, if we're going to use this approach, we need to be able to build a random number generator which produces draws from the right density. So how might we do that? Well, here's a very funny looking density that I made up based upon, it's a horseshoe shaped density, and it's what I'm going to call a target density, bold P. I want to pull draws from this density, which is only two-dimensional in this particular case. Can I do it? Well, yes, here's a random number generator running, which is pulling draws from that density. You can see it's pulling more draws here in areas of high probability, but does come down every now and again to pull draws from areas of lower probability, and it stays pretty much within the support of this density here. How did I achieve this? Well, pretty clearly I've initialised at some point here, and I've looped for as many times as I want realisations from my random number generator. Each time through the loop, I've done some very simple things. All I've done is randomly perturb the current realisation from the random number generator to give me a candidate new one. And I could do that from a fairly arbitrary density, but here I've just chosen a random walk. I've just put on a little Gaussian perturbation here. That gives me a candidate for the new realisation for the random number generator, which I don't necessarily use. I decide whether or not to use it to see if it's more likely to have come from the target density or not relative to the previous realisation. If the candidate is more likely relative to the previous realisation, I definitely keep it. I always keep a good one. But if this ratio is less than 1, it's not as likely to have come from the density, I don't necessarily throw it away. Otherwise, I would never traverse down through this density and then come back up again and properly explore it. I keep realisations that are worse than the previous one with probability alpha. This is called the acceptance probability. And implementing that is easy. I just draw a realisation from a uniform density, I compare it to this number alpha, and I either keep the proposal or not, depending upon whether it's less than alpha. So the point is, the operations here are quite simple. An evaluation, draw a random number generator, and a compare. It's not a difficult algorithm to implement. And then I keep looping until I've got enough realisations. Why does this work? Well, it works because it's an example of what's called the metropolis algorithm. It's specifically designed to implement a Markov chain. These draws are coming from a Markov chain, which you can visualise abstractly as one of these things that we see in all our textbooks on basic probability. And it's a Markov chain where I know what the transition kernel is. The probability of moving from this value to this value is the probability that the value is proposed times the probability that it's accepted. So it's very simple to work out what this transition density is. And the transition density pretty much characterises a Markov chain. And what's important to us is that the probability of being in any state in this chain that we're constructing changes with time. Here's the density for sample I. Here's the probability of being in a state at sample I minus 1. And the two are related via a recursive relationship here involving an integral with a transition density. So it's something we can characterise. And the question is, will this ever converge so that as I changes, the function itself doesn't? I converge to a stationary density. And moreover, will the stationary density I converge to be this target density that I'm actually interested in? Well, for that to happen, P would have to work on both sides of this integral equation. So if I'm going to use this Markov chain theory to design something which spits out things from a given target density P, it's going to have to satisfy this integral equation, which looks quite difficult to achieve. Let's see if it does achieve that. Let's concentrate on the integrand here. The integrand is the probability of moving through the chain from theta to xi, given that I arrived in theta with my target density P. What if I had a chain where I was just as likely to do that in the forward direction as in the backward direction? Chains like this are called reversible chains. Well, if I had one of these chains that was symmetric, then I could replace this probability with this one because it's the same to go backwards. But now I've got something here that doesn't depend upon the integrating variable, so I can pull it out the front. I'm left with a probability density area, which must be 1. And hey presto, I'm solving the integral equation that I need to. And that's how the Metropolis algorithm works. This acceptance probability, that simple ratio, is specifically chosen to make this path have equal probability to this path, which then automatically gives you the target density as being what the chain converges towards. I think it's an amazingly clever technique. It goes right back to the 1950s. It was invented as part of the effort to develop the hydrogen bomb. The early paper on this has got Edward Teller's name on it, and the roots actually go further than that back to John von Neumann, who was one of the first people to look at ways that computers could be used to do computations using randomised algorithms. So how might we do that for our simple fourth order example? Well, there's two things we need to worry about: the acceptance probability and the proposal. Let's look at the acceptance probability. I need to be able to evaluate from a target density, which in my case will be this posterior of the parameters given the data. So how can I evaluate that? Well, first up, by Bayes' rule, I could say, well, that's the product of the likelihood times whatever prior I want to impose, and divided by a normalising constant to make sure the area underneath this thing on the top is 1. Except that crucially here, because I'm taking a ratio, whatever this normalising constant is will cancel, so I don't need to compute it. And hence I avoid the need for a nasty multidimensional integral here. So this is very important. So I only really need to worry about what's on the top here. We know how to compute likelihoods. That's bread and butter for us. It's simply the product of these prediction densities. What's the prediction density for that fourth order example? Well, key to it was the fact that the density of my additive noise here was an indicator function from minus kappa to kappa. So this likelihood here is nothing more than the product of indicator functions evaluated at the difference between the observed response and the modelled response. So a very simple calculation. Put a theta in, simulate it, compare it to the observed response, throw it into an indicator function, product it all up. Multiply by a prior, and you've got what you need here. So that's not hard to do. What about this proposal here? That's the second step that I need to design. Well, to discuss that, let me go back to my horseshoe example because it's easier to illustrate some points on that one. The exact random walk that I used there was one where the additive Gaussian perturbation I used from a random walk had variance 0.2. And if I look down on that horseshoe, here's the trace of how I explored this density using that proposal. And if I look at the traces versus time, here's what they look like for the two x and y axis parameters. And you can see they're moving around without too much correlation, so they're likely to work well in some sort of averaging relying on the strong law of large numbers. If I choose the variance a lot smaller, then I take lots of teeny tiny steps that all get accepted and I explore my density quite slowly. And if I look at the traces, I can see there's lots of correlation here, which is bad for strong laws of large numbers. As the correlation goes up, the convergence rate goes down. So this is not a good choice. Vice versa, if I make big choices, then I make lots of big steps which get rejected. And the traces, once again, are very correlated, albeit in quite a different sort of fashion, but I won't get good convergence. Here, I'm proposing things that are too small and too many are getting accepted, too big, too few are getting accepted. You need to tune this so that you get about 40 to 50% is the considered rule of thumb of your proposals being accepted. So you explore your density well without getting too much correlation. But this is a tuning parameter that you need to choose, and it's a very active research area in the statistics community for how you might choose this automatically without having to hand tune it. Okay, so that's how I computed my multidimensional integrals on that fourth order example. I used the Metropolis algorithm to get random realisations, and then I relied on a Monte Carlo approach to compute my integrals. So that's how this posterior density was computed, that's how the posterior mean was computed, and remember the red was the true value. I had to run 1 million iterations from my Metropolis Hastings algorithm to get results of this quality. And after coding it up in C and running it on a 3.7 gigahertz serial CPU, I managed to do that in a magical minute. So it's a big multidimensional integral, but it's not unfeasible for us to do that with current computing power. And it might be something we might want to include in our system identification toolbox. These posterior densities for the phase margin, well, I computed them for each of the 10 to the 6 realisations of systems that I had from this density. I computed the phase margin for each of them. And this is the sample histogram of the achieved phase margins. I didn't code that in C. I used a MATLAB M file. It took 10 minutes. But I think you could get it going a lot faster if you did go to the trouble of coding in C. So I think if we recognise what's available to us just on our desktop PCs, there are some new things we might want to have a look at in the area of system identification. That's in the linear case. I'd like to turn to the final thing that I mentioned at the start, which is, well, what about new and expanded model structures? And once again, I like concrete examples, so here's a concrete one. It's a particular nonlinear system where there's a nonlinearity in the state update, there's a time variation in the state update, and there's some noise entering in the state, and as well there's some nonlinearity in the measurement equation. So for this model there's 4 system parameters and 2 parameters quantifying the stochastic components to be estimated. And this example is widely used as a test case in statistics and econometrics. I think it's important or interesting that, as far as I'm aware, this test case actually has its origins in this conference. Thomas Schoen is a clever enough detective to have found this paper from the 1978 Ifac World Congress in the Linköping archives, which introduces this example. It doesn't reference it as having come from somewhere else, and it doesn't explain where it came from. If anyone in the audience is able to give us an earlier reference, we'll be fascinated to hear it. But we think that actually an example that's being used in other fields is something that our community actually contributed. So the point I wanted to get to is I clicked the wrong way. How might we estimate a system of this sort? Can we address this with our current suite of tools? Well, to address that, let me actually be a little bit broader. That's an example of a system which has got a general nonlinear equation for how state, input and noise affect a state update and how state, input and noise might affect a measurement. If I wanted to estimate a nonlinear system of this type, and hence the example I just showed you, well, first port of call would be, can I compute a likelihood and then try and maximise it or use it to compute a posterior distribution? And I'm immediately then faced with the problem of, well, how would I compute these prediction densities? Well, in principle, I can do this. There are general measurement and time update equations which will allow me to do it. To begin with, if I've got a prediction density at time t and I want to update it to a filtering density at time t, I need only multiply by the measurement probability at time t. But then this numerator does not necessarily have area 1 underneath it when integrated with respect to x, so it's not necessarily a bona fide probability function. So I need to divide it by a normalising constant, which is the area underneath that. So once again, I've got a multidimensional integral to compute. This will be of dimension equal to the state vector. And when I do compute this normalising component, you can see that by the law of total probability, it's this prediction density that I actually need here. So the normalising constant is the prediction density I'm after. These two equations together are called the measurement update. I need to be able to apply this recursively, so I need to now be able to take this filtering density at time t and update it to a prediction density at time t plus 1. And again, I can do that using the law of total probability, but I'm going to need to do a multidimensional integral again. This is called the time update. So if I'm going to try and employ this sort of strategy to estimate a nonlinear problem of this type, I've got a computational issue on my hands. I need to compute two integrals of dimension equal to the state, capital N times, where N is the number of data samples I've got. So this looks quite daunting. How might I do it? Well, it turns out a particle filtering approach, a Markov chain, a Monte Carlo approach to integration, which is known as a particle filter, can help me here. And many of you will know already about what particle filters are, but I want to just present some detail so that I can talk about computational issues associated with them later. And hopefully it's also educational for people who aren't so familiar with particle filters. So the idea is, I want to somehow come up with a random number generator that gives me draws from the prediction density at time t, then gives me random draws from the filtering density at time t, and updates them again to the prediction density, but with time stepped on by 1 point. And here's the first typo on the slide. That should be t, not t minus 1. I'm very sorry. Achieving that happens to be very simple. The operations involved for achieving this aren't complicated. Let's suppose I start off by having draws from a random number generator from this prediction density at time t. I can use those draws as an alphabet from which possible draws could be taken from the filtering density at time t. And the way I use this alphabet is that I sample from it with replacement. And the way I sample is I consider whether the filtering density, a particular particle here, would lead to the observed output being likely or not. If for a given element in this alphabet, the probability of the observed y is highly likely, then I'll choose that member of the alphabet with high probability and hence probably several times. Vice versa, if for a given member of the alphabet that I plug in here, the probability of the observed output is unlikely, I sample it with low probability, and hence I might only get one sample or perhaps even none at all. Once I've got these samples from this density, it's equally simple to propagate them on to get samples again from the prediction density, but with time moved on by 1. I simply do a simulation. One by one, I take these samples or particles, plug them in to the state update equation and do a simulation that involves simulating a random realisation from this noise and plugging into this formula. And so these then get simulated to various points here. And this process can be repeated over and over again to give me a recursive way of generating random samples from the densities that I need. There's variance on this particle filter, but this is the basic flavour. What does it look like? Well, here's our simple example again. The blue here is a state trajectory for a simulation I did of this system. And the draws down here are from the filtering density at time t equals 1 at the moment. It will progress with time in a moment. So these are the random draws from a random number generator from the filtering density at t equals 1. And if I average across them, I'll get a Monte Carlo approximation for the integral, which is the conditional mean at time t equals 1. And you can see it sitting here. If I let this run, you can see these random samples from the filtering density change as time evolves, and hence the averages over them change, and so my state estimate changes. And I think you'll agree, while it's not a perfect estimate of the state, it's doing a reasonable job. And I hope I've established that it's fairly simple to do this computation. So all this machinery now gives me a possibility for how I might address that nonlinear estimation problem. I want to compute, or I need to compute, this prediction density, which by the law of total probability is given by this. And via a particle filter, I can get random draws from this prediction density here. So if I just take those random draws, plug them into my measurement probability equation and take the sample average, I'll have a Monte Carlo approximation to this integral, and hence to this prediction density. I can use this approximation, which I'm going to call p hat, to now compute the likelihood just by producting them all up together, and then the posterior mean that I need to evaluate just by normalising, multiplying by whatever prior that I have. So this would give me a means, at least in principle, to do exactly what I did for the linear case in the nonlinear case. I'd run a Metropolis algorithm where at each step, when I needed to compute this acceptance probability, I'd use my estimate of the target density formed via this particle filter Monte Carlo approach. I can hear you saying, yes, Brett, but that's completely ad hoc. How have you got any idea that that might work? And I'd agree with you. It is quite ad hoc. Sure, this algorithm will give me a whole bunch of draws which I can call theta and compute histograms of, but what are they really histograms of? This realisation here depended upon a particle filter approximation, which itself depended upon some sort of random event. And similarly, this sample here depended upon a particle filter approximation, which depended upon another random event. So what I'm really looking at here, I've really got two random events going on. Random events which I don't see, which affect the particle filter and hence the sample that I've got here, and random events that I do see. And I can model that by saying, well, what I'm really simulating here with this seemingly ad hoc approach are realisations from some joint density. I don't know what that joint density is. I'm hoping it's going to be the target I'm after, but at present I don't know what it is. And in fact, there's part of it that I don't even get to see realisations of. I only look at these realisations here. Well, that's marginalisation. I'm marginalising. So in looking at these realisations here, I'm seeing realisations from a density which is the marginalised version of this joint density here. And the $64 million question is, well, what is this density which is the marginalised version of this? Is it something good and useful, or is it just completely unrelated to what I'm trying to compute? Well, that question has been answered very recently in a paper in the Journal of the Royal Statistical Society, which I'll show details of in a moment. In fact, this marginalisation is equal to the expected value of your estimate here that you used in the Metropolis algorithm. And so if that estimate happens to be an unbiased estimate, then this density here will converge to the target density I'm after, even though I'm using randomised approximations in the algorithm. So there is a theoretical basis for doing this. It's not completely ad hoc. There is a theoretical argument that says you will still be generating realisations from the right density, or the density that you're after. Now, the paper involved, as I said, just came out in the Journal of the Royal Statistical Society in the middle of last year. It's by Andrio, Doucette and Hollenstein, and these may be authors that many people here in the room are familiar with because they've made many contributions in the area of particle filtering. There were at least roughly 20 discussion papers associated with this, so it's quite a high-profile paper. And the reason they wrote it is because in other areas of science, people are already using this algorithm that I just mentioned to you. I didn't make it up. I stole it from other literature. Here's an example of a paper in the area of oceanography where precisely that algorithm is being used to estimate parameters in models for plankton growth and death. Here's an example of a paper in econometrics which is using precisely the algorithm I just showed you for looking at models that are pertinent in that field, and in particular stochastic volatility models. Here's a paper from Nature which discusses data that was generated via not exactly the algorithm I showed you, but one that's very, very closely related. And finally, here's a paper that comes from the Notices of the Royal Astronomical Society that is trying to fit models in the area of cosmology using a very closely related variant of the algorithm that I just proposed. So the message is that our scientific colleagues out in many other fields are addressing what we would call system identification problems, but with respect to model structures that we can't yet routinely handle within the suite of tools that we know and love. And I think we could probably learn something from that and from our colleagues by looking at what they're doing and seeing how we can adapt it to our needs and purposes. So let's return to how that whole scheme works back on our example. Can we estimate parameters here? Well, I'll skip forward just a second to our magical minute. If I run on my single thread 3.7 gigahertz CPU, after a little over a minute, which allows me to do 64,000 iterations of my Metropolis algorithm with 256 particles in my particle filter, these blue lines are my histograms, or smooth sample histograms for my marginal posteriors. You can see no one would say that those have converged. They were very different to what they were just a time sample ago. They're still quite rough. You couldn't trust these conditional means as being the true conditional means. You need to keep running. So here we are at 5 minutes, 16 minutes, we've got the hint of convergence going on. After about an hour, I'd start to get confident these might be the right histograms and the green posteriors might be useful. I think it'd take to about 3 hours before you'd start to really think, yes, I've converged and I could use these answers. And if you continue for a day, you can be extremely confident that you've got to the right answer. So the good news is, it looks like this method could address some areas of nonlinear system identification which might be useful to us, but not within a minute. And that's, of course, because of the huge computational load. I had 100 data samples. For each of them, I had to run 256 particles, and I had to do that every time I ran a Metropolis iteration. And I had to run 2 million of them to get a reasonable answer. And each time I did that, I needed to use some CPU cycles to compute acceptance probabilities and so forth. So if you add all that up and divide by the CPU clock rate, sure enough, you get to 2 hours. And this is sensitive to the amount of data. If I suddenly had 1,000 data samples, I'd be out to 20 hours here. So I can hear you saying, well, Brett, this is all very interesting, but I'm going to need a supercomputer to do this, and I don't have a supercomputer. Well, I'd agree with you on one point. Yes, you do need a supercomputer, but disagree with you on the other point. You can have a supercomputer on your desk very simply, and this is what it's going to look like. This is the top-of-the-line NVIDIA graphics processing unit, which you can plug into a desktop PC, GPU for short. It contains 512 floating point cores that run at close to 1 gigahertz each. It's got a memory bandwidth of 200 gigabytes per second. The current generation Intel chips have got a memory bandwidth of 20 gigabytes per second. And it only consumes about 150 watts. It's cheap. You can buy it for $450. And as a side benefit, you can play Call of Duty Black Ops in its full glory with everything cranked to the max when you're not doing difficult system identification problems. I think it's interesting to look at how the capacity of these sorts of cards has increased over the last decade relative to desktop CPUs. These are Intel desktop CPUs, which I chose just because I could find information on them in order to draw this graph. There has been an increase in the flop performance of these CPUs, even though the clock rate hasn't gone up, because of the multi-core capacity that they offer. But this has been completely outstripped by what's been available in GPUs. So this current generation GPU, if all the cores were fully utilised all the time, you'd be looking about 1.6 teraflops of performance. If you go back a decade, the world's fastest supercomputer, ASCII Red at Sandia National Labs, had an achieved performance of about 1.35 teraflops. Now, I should emphasise this is achieved rather than theoretical. This is actually on LINPACK benchmark, so is probably quite a bit below what the theoretical is. But nevertheless, I think it gives you a navigation point of what's available here relative to a decade ago. Of course, it's nice to have that capacity. Can it be used? Can I program these cores to do something useful? Yes, you can. NVIDIA supply an API whereby you can access those cores, do whatever computations you want, get the results back. The API is called the Compute Unified Device Architecture, and it's so well recognised that this capacity should be utilised that you can go away and do university courses now, and you can do it for free. You can go to iTunes and you can do the Stanford course on how to program those devices. If you don't like the Stanford one, there's a Harvard one also available through iTunes, and I'm sure there's many others on the web. So this is not something particularly sophisticated. It's entering into the mainstream, and hence I think it's something we need to pay attention to in system identification. In case you're wondering if I'm getting commissions from Stanford or Harvard or NVIDIA, if you don't AMD Firestream cards will do the same thing for you. There's an API you can use for programming them as well. It's called OpenCL. This capacity, as you can imagine from the lectures that are becoming available, is being used by a lot of people in science and engineering. There's a web page that's maintained at NVIDIA, and it currently profiles over 1,000 projects where researchers have taken the time to post their profile up on this site. So once again, the message is our colleagues out in science and other fields are recognising this capacity and are employing it. Thanks, mate. Again, this is only useful if we can map our algorithms to take advantage of these particular structures that facilitate parallel computation. Well, happily, the Metropolis algorithm is quite simple to parallelise. Whether I run one long chain to get my 2 million realisations that I need in my average, or whether I run a whole bunch of shorter ones, of shorter length, to still get a total of 2 million realisations, makes no difference to the accuracy of my answer. It's just that I could do these shorter chains all in parallel. And in principle, I could run as many chains as I have processors. So I could get a linear speed up in the number of processors that I've got. Except for the fact that I might not start each chain in the right space. I might not put it within the support of the density I'm after, so I might need to throw away some realisations that it takes me to get inside the support. But balancing that, if I initialise these parallel chains independently, I get more independence across these samples, which is good for convergence. So the message is, the Metropolis part lends itself very nicely to using parallel architectures for speeding things up. Particle filter, well, some of that lends itself very nicely. The update from filtering density to prediction density, which as you recall is just a simulation, I can assign one core, which I'm symbolically representing here in purple, per particle and get a linear speed up with the number of processors that I can assign to this. The sampling step, there's a little bit of a hitch. You might have noticed that I squibbed things a little bit where I just had a proportional to here. I didn't say exactly what the density is. Well, that's because I'm treating this thing here in its second argument as a bona fide density. And of course it's not. There's no guarantee that if I integrate over this second argument, I necessarily get the answer 1. Before I use this, I need to work out the appropriate normalising component. And that's a summation. So potentially, I'm going to have a bottleneck where I need to sum over a whole bunch of particles at one point. But of course I can be smarter than that. I can assign multiple cores to these particles. So suppose I've got 16 particles and I assign 8 cores, 1 to each pair of particles. Then I can do a summation of pairs in each processor and pass it on to 4 processors, then 2, then 1. So if I use a tree-like structure, instead of taking 16 time steps to do my addition, I can take only a logarithm of that to do my addition. I can turn a potentially order m number of CPU cycle computation into a log m1, which is a very significant speed up. So there are speed ups available. So both the particle filter and the Metropolis algorithm can both take advantage of these parallel processing platforms. So we've experimented with that. We mapped that previous algorithm that I showed you on a serial architecture, the coupled particle filter Metropolis algorithm, onto an NVIDIA GTX 560. When we bought it, the 580 wasn't out yet, so it's not the top of the line one. No Call of Duty cranked to the max, but still useful for system identification issues. After we ran 64 chains in parallel at each time, and after a third of a second, here's how our histograms evolve. And we're hoping, we've just missed out. We've got to the magical minute, and we still haven't quite converged. But I think you'd trust me from the graphs that I showed you that if I just wait 6 months, a new NVIDIA card will probably be out where I can map it to more cores, and I probably will make this within a minute. Or even nowadays, I could just plug another NVIDIA card in. I can have 2 in at one time if I want, get the number of cores I need, and I could get this in under a minute. Let's keep going. After 17 minutes now, I can trust that I've converged. It was hours before. This is 320,000 iterations times 64 chains. That's equivalent to one chain with 20 million iterations in it, which previously was taking me 8.7 hours. On a top-of-the-line serial processor, I'm now getting the answer in 17 minutes, which is a speed-up factor of 31. So I think it's taking algorithms which look infeasible or not interesting to us and potentially making them a tool that we could have in our toolkit as system identification people. So what are my conclusions after going through this tour of thoughts and examples? Well, I think it's a very interesting and in fact vital question for us to consider how we're going to expand our capability in our field to perhaps start contributing through to other fields and having a higher impact and making it easier for us to get grants in our area and keep our research careers going and having an important impact in engineering and science. I think we could do that by looking at new methods, and I've just posed one example by looking at Bayesian approaches. I'm not suggesting that that's the best or only example, but I think we should be looking at new methods. I think we should be looking at new model classes and expanded model classes that we can address. And in doing so, I think it's going to be vital to do what people in other fields are doing and recognise and exploiting the advances in modern computing architectures that we've got available to us. So we should learn from our friends in other fields. What are the challenges? Well, one challenge, which I've just talked about in detail, is if we're going to come up with new methods, they're going to have to map onto the architectures we have available to us. They're going to have to be parallelizable. We're also going to need good software support. If you say to me after this, look, Brett, I was interested in that fourth order linear example, can I have the code? I'll be very happy to email it to you and you can play around with it yourself. It's written in C and it will run on we can give you a version that will run on your Windows or Mac or whatever processor with no problem. If you ask me for the code for the nonlinear example, I'm happy to give that to you as well, but you'll need to have exactly the same graphics card as we used for it to run. It exploited the fact there were 384 cores. If you have 512 cores, some will go missing. If you don't have 384 cores, it won't run. If you want to change the model structure, you're going to have to go into the code, change it yourself in C, recompile it, link it against the right API, download it. It's going to be complicated. It's not at the level where we have quick and easy software support to easily use these hardware that are coming available. So that's a challenge to us to come up with those tools. Many thanks for coming along to the talk when I know it's the end of the day and everyone's very tired, and thanks again to the organisers for allowing me to present this talk. Special thank you to the Signal Processing Microelectronics Group at the University of Newcastle, who endured a few versions of this talk before this one and were instrumental in putting it together. Thank you very much.
Okay, thank you very much, Brett, for a very clear, according to me, a very thought-provoking lecture here this evening. A few philosophical things that I picked up from your speech. That's one is the question, what do we do with our time? And of course, there are several options. You gave the options that we could do some gambling, but we better do it in a smart way, if I understood from your methods. Two other things. The relation with adjacent societies you mentioned. There are developments in other societies going on that really come close to what we are interested in and what we are doing. And I think you gave some very nice examples that it is very important to look around in our field and look at, particularly also at the statistical field, to look at what developments are going on over there. And of course, you've clearly shown that the computational capabilities that we have nowadays and in the future will definitely influence the way that we think about identification problems. And in that sense, I think you made a great contribution today. I'd like to ask the audience to give you a great hand again for that. Brett will be around the rest of the week, so you can address him with questions outside the scope of this lecture. I would like to close the session now. Thank you.
Very cool. Thank you.